have the floor.
So thank you very much for the introduction. Just 1 second and I will share my screen. Yeah, so can you see it?
Yes.
Okay. So, well, I'm very happy to be here and thank the organizers for giving me the opportunity to present our project. And I think that it's a nice link to the project that was just presented, because it also deals with macroalgae and it also has some biofilm parts. So I will very quickly introduce you the project. So as it was said, I'm a researcher at the Institute of Agrochemistry and Food Technology, which is the largest institute of the Spanish National Research Council devoted to food research. And in this project, we have collaborated with groups from the Chagas, from Nofima, from the University of Hohenheim and Rice, as we wanted. So each of the groups had a different expertise to tackle this project. And as you all know, seaweeds and seagrasses are very interesting but underexploited materials. So here in Europe, macroalgae are mostly used to extract phycocolloids, as our colleague from the SEAMSA was telling before. But the amount, so the percentage of phycocolloids that are present in these macroalgae is relatively small, so around 20, maximum 30%, and the rest is a residue. And moreover, the procedures used are traditional procedures, and we thought that the efficiency of the processes could be improved. So the main objectives of our project were, first of all, to evaluate novel extraction procedures, so combining these traditional processes with ultrasounds, microwaves, or enzyme-assisted extraction for obtaining these phycocolloids or hydrocolloids. But also, to valorize the insoluble residue of these seaweeds and also of seagrass, which I will show you later, to obtain biodegradable materials. And what we wanted to check also is to analyze all these processes from a life cycle perspective, which was done by our colleagues at Rice. So a very quick overview of the different species we have worked with. So a red seaweed, Gelidium sesquipedale. In this case, this one is not for carrageenan, but for agar extraction. And we obtained agar-rich extracts and also lignocellulosic fractions from the residue. We also work with 3 different brown seaweeds, which are rich in alginate. So we obtained alginate-rich extracts, but also lignocellulosic fractions. And we also explored a very interesting seagrass, which is endemic from our Mediterranean Sea, for obtaining lignocellulosic fractions and also bioactive extracts. So the strategies that we followed in the project to make the processes and the products more sustainable were, first of all, as I told before, this evaluation of these novel processing techniques, but also to simplify the processes. So that is to eliminate some of the purifying steps to make the processes more sustainable, and also kind of to mimic nature. I mean, in nature, we have a combination of compounds, and some of the compounds give certain functionality. So we thought that obtaining less purified extracts could also result in extracts with additional functionalities. And to make more sustainable, even more sustainable, these processes, we also checked on residual valorization. So very quickly, I will show you some like the highlights of the project. So regarding the novel processing techniques, we have seen that ultrasounds greatly increased the yields. It's a very promising technique to be incorporated in these extraction processes. We also checked on better LCA of the processes, both for red algae and for brown algae, so for agar and for alginate extraction. But there's more work needed for scaling up these technologies. And there's also lacking a cost evaluation of these new processes. So how much cost would be including this ultrasound step. Regarding the simplification of the processes, in here we have obtained really interesting results. I have to say that the extracts obtained cannot be used for the same applications as pure agar or pure alginate, but there could be new potential markets for these less purified extracts. And we have tested, for instance, their potential as encapsulating matrices or alternative packaging films with better water sensitivity than the pure alginate films, for instance, or agar films. And we've
you only have 1 minute left.
Okay, so and we have developed a couple of patent applications, one related to aerogel development from cellulose from the residues, which are very interesting, very porous and highly sorbing materials, which can be used for a broad range of applications, including food, but also pharma or biomedical. And this patent has been selected for an acceleration program. And another patent, which we got another project granted for scaling up the process, and we managed to scale up these extraction, simplified extraction processes, and to produce biodegradable packages from these residues of Posidonia oceanica. And what I have to say is that another very interesting result is that we have made a very deep characterization work on the residues from the algae after agar and alginate extraction. And I must say that there's a whole world to discover, because these residues are very rich in other compounds, which could be used as ingredients for food and feed applications, as new materials for packaging or biomedical applications, or even as bioactives for pharma and food, for pharma and cosmetics. So our future challenge is to further investigate these residues and also to take all these developments from lab to society. So we are open to discussions with companies which could be interested in that. And if you want to know more about our project, you can always check our webpage. And thanks a lot.
Yes, thank you, Amparo.